Now in this part we're really going to prove this y-axis. We now know it's a continuous. We proved that this function actually satisfied this integral equation. Now I want to recall from the earlier video that our nth iteration can be written as the sum of this gk. Of course gk is tautologically defined like this, but good thing about it is that we have a nice upper bound on this gk, which is stated here. This one, absolute value of individual term, is bounded by this nice expression with a factorial down there and kth power of this m2 times x minus a. Now let me remind you of what we wanted to prove. We wanted to prove the function y-axis, which is defined as a limit of this one, satisfy this one, this integral equation. So what we're going to do with it, we're going to start with the Picard iteration relation. And how do we pass from that Picard iteration to this y-axis is taking the limit. Put the limit in the left-hand side and put the right-hand side. We'll also put this limit n approaches infinity, and be a little bit careful with this integral operator. So here is the Picard iteration relation, and we're going to hit limit n approaches infinity here, limit n approaches infinity to that side as well. So if you do that, we have simply this expression, and since this is the constant, we'll think about this limit acting on this integral. This is, again, I've shown this a lot in this differential equation in Calculus 3, and this is the part something you have to be careful, and since the proof is not complicated, I will repeat it again, but this is the deal. This different order of operation that you're doing the integral and limit later versus limit first and integral later. Can we swap these two? It's a different order of operation. If you think about existence of many different order of operation, that makes a difference. You have to be careful in here. But left hand side is simple by definition. This is supposed to be y of x. For fixed x value, this is supposed to be the value y of x. You just have to think about this part. Now of course what we want is that this limit can go inside and change that yn to yn here. So what we want to show is that integral first and limit later is the same as limit first on here, so that changes to yt, and integral later. So that's how you interpret this left hand side and right hand side. So mathematicians have proved this type of statement in the following way: to take out the limit and compare this quantity and that quantity by taking the difference and show this approach 0. Then it proves that these two things are equal to each other. Now if you look at the difference, and limits of the integrals are the same, so you can bring it into a single integral. So this part is inside the single integral, and here, and I'm passing to the absolute value of inside so that it gets bigger. Now this one, you're looking at it again, the function difference of same function value, and then it triggers you to think about the mean value theorem. So we apply mean value theorem here. So this one is exactly equal to the sum mean value, the value of the partial derivative at y, times the difference of input value yn and y here. It's yn minus y. Again, this yn tilde is in between yn and y, so it's in the box. Think about it, if yn is supposed to approach y, if n is big enough, and that's definitely close to each other, so we can assume these things, yn tilde is in the box. So that is replaced by m2, and we're going to keep this value there. So that's how it looks like. Now m2 is out there. All we want to show that this whole thing approaches 0 is tempting that, okay, yn approaches y, therefore inside approaches 0, therefore this integral of 0 is going to be 0. But if you think about it, that's again the order of operation. You're doing this n approaching infinity after you did doing this integral. So here the whole point is that not being sensitive about this order of operation. So here you have to be sensitive there as well. So think about it, and you can't just send this one into 0. That would mean that you're doing the limit inside first and integral later. So you have to be careful here. Now let's think about what this y and yn are. y now can be written, because we know it exists in this form, we can write it as infinite sum of values of gk. And yn is the term up to n. So if you subtract these two, then it's going to look like that, except the sign here. I didn't think about the order. So it truncates up to nth part, and this has all the infinity. So this part starts from n plus first index and to the infinity. So now if you compare it with this one here, and this one with the absolute value, and then can be replaced by this expression with even greater than equal to symbol, because if you put absolute value around it here, and if you put absolute value inside the gk, it gets bigger. Now at this stage we can replace with what we know about this upper bound of the gk, which we calculated in the earlier part. So that upper bound was this absolute value y0 divided by k factorial with this kth power. Now we're going to replace this even with this has t in it, with the largest possibility, which is beta minus a. This is a typo as well. This is supposed to be a plus beta. T goes all the way up to, at max, a plus beta. Right, didn't look good, so I fixed it. Now this is a plus beta, and now this part is replaced by just inside here is the beta. It's the beta k. Now if you think about this entire quantity with this maximum possibility replaced, this is just independent of t. There's no t in it, so this whole thing is now a constant. It can be factored out here. So it leaves this invisible 1 inside the integral. Now this whole thing, if you think about it, is again just the tail part of the expansion of this exponential value. So since this starting from k equals 0 infinity exists to be this number, and if you look at the tail part, as n approaches infinity, this much must approach 0. And this part is just simply x minus a is constant. Now what is varying here? So up here I pulled up the statement that we started. We wanted to conclude that this integral and limit outside is actually equal to this integral value, and the difference between these two things is now estimated by these calculations to where x is fixed and only n is approaching infinity. So n is only occurrence in this here as n is in this spot. So as n approaches infinity, that goes to 0, while x and a and m2 are all fixed. Therefore, the claim is true. So that established the statement. When you hit this, the Picard iteration equation, and if you hit limit n approaches infinity both sides, left-hand side becomes yx, and right-hand side, that limit outside now can go inside with that justification we just went through. So it does satisfy the differential equation, which is equivalent to this integral equation. Initial condition is a lot easier. If you plug in x equals a in there, integral a to a is going to be 0, therefore just simply y is 0 here. This proves the existence of a solution to that initial value problem.